The last talk before lunch is by Hanno Rein on the validity of the superparticle approximation of planetesimals in simulations of gravitational times.
Thank you. So I'm doing a PhD next door together with John Pavloisu, and I'm usually working on multiplanetary systems. But I've done this project together with Geoffroy Lesueur and Zoe Leinhardt, who are both here in the audience, on planetesimal formation, and we're looking at the gravitational collapse that happens in the formation process. So let me just summarize this idea that Johansson et al. Had in this 2007 Nature paper, how to form planetesimals in a turbulent disk. So you start out with a turbulent gas disk where the MRI is active, and you've got meter-sized particles in your disk. And the MRI creates an overdensity in the disk. And if the overdensity is large enough, then the streaming instability can kick in. And the streaming instability once more creates an overdensity. And now we're in a regime where the density is so large that the material can become unstable, gravitationally unstable, and simply collapse to a bound object, which is then called a planetesimal. Now what we're doing, we're looking at the final stage in here. So we're only looking at what happens if you have an overdensity. This becomes gravitationally unstable, and you get a planetesimal out of it. So we're really looking at this zoomed-in picture here on the very high density regions. Okay, so what kind of order of magnitudes do we have in the system? Well, there are a lot of particles in the whole disk. There are 10 to the 24. They are all meter-sized particles. That's what has been assumed. That's what I'm going to assume. Now you can argue whether that's too big or too small or whatever. I'm going to come back to that later on. So for meter-sized particles, the gravitational scattering will be not important, right? If you have two meter-sized particles, they will never gravitationally interact directly with the inner two-body system. So you have to keep that in mind, because if you model it numerically, this can become important. Then I'm assuming that the stopping time, so the interaction timescale with the gas disk, is of the order of one orbit, simply in Epstein track regime. And I'm also going to assume that the collision timescale will be of the order of a few orbits. So the timescale of two particles interacting with another particle physically, with a physical interaction, will be a few orbits. And I'm going to justify this a bit more by putting in some real numbers and calculating the timescales. So I'm going to assume a canonical value of 1 AU, a surface density of the gas of 150 grams per centimeter squared, which leads to a volume density of 10 to the minus 10, and the sound speed of a few hundred meters per second. I'm also going to assume that there are a lot of solids in there. So the material of the solids, the mass of the solids is approximately the mass of the gas in the disk. Because this is what you get in this chain of instabilities that I presented you above that create this overdensity. So at some point you have a value which is close to 1, that ratio. And I'm going to assume a particle density of 1 gram per centimeter, so just water. And my particle size is 1 meter. And my velocity dispersion of the particles is 30 meters per second. So most of those simulations, most of those parameters come from Johansson's simulation. Now when you take those numbers and calculate various timescale, it gets interesting. So first of all, as I said, the Epstein track, the stopping time, is of the order of 1 orbit. And then you can calculate the collision timescale, and this will be of the order of a few orbits. So here it's 80 orbital timescales. But notice that here's on the bottom there's a rho p, so that's the density of the particles. So the more particles you have, the more collisions you will also have. And this number will go down once you increase the particle density. Now just to show you that the gravitational scattering is really unimportant, if you plug in the numbers, you get a timescale of 10 to the 21 orbits. Okay, now I'm going to talk a bit about collisions. Now these are meter-sized particles, so you can't tell us what's happening. I'm going to make a very simple argument about what the nature of those physical collisions is. So if we assume they are completely destructive, every single collision is destructive, then we're going nowhere, right? We would just grind them down to dust. And the next thing would be perfect merging. They just stick and form a bigger particle. But there is, after all, this meter-sized barrier, and we can't grow beyond that size. Otherwise, we would spiral into the star, or we would need the whole mechanism in the first place. It's a bit of a circular argument, but if you assume that just everything merges, you don't have to do anything. And then what we're left with is something like an elastic collision bouncing. And out of those three possibilities here, I would argue that in most cases it will be something like an elastic collision in the disk. So the particles basically remain their size. Obviously there's a coefficient of restitution there, and they're going to lose material and they're going to grind down a bit, and it will be a mixture of all of that. But the average thing will be something like that. I will justify this more at the end of my talk. Okay, so that was what happened when two particles collide. Now what happens if a whole cloud of particles collide? That is something that you will have in the gravitational collapse. You will start with some axisymmetric tumor wavelengths in your box, and they will contract. So you will have particles, clouds approaching each other. Now, when this system is marginally collisional, which means that you have one collision per dynamical timescale, then some of the particles will have a collision and others don't. And when the two clouds collide, you're left with something that looks messy. So you randomize your velocities. Right? This is a bit counterintuitive, because if you have a lot of collisions, then you wouldn't see that. They would just damp and stay on top of each other. But since here you have one collision in the whole process, it's different. And I'm going to show you what has been done so far, how it was simulated. And I think this is not a good way of doing it. So people are using superparticles. Superparticles represent the distribution of many particles. Well, we can't simulate 10 to the 24 particles, so we have to do 10 to the 6 or something like that. So every particle in our simulation really simulates 10 to the 18 particles. Now what happens if two of those superparticles collide? Well, then if they are close together, they feel a drag force. That is simply due to the energy loss in the collisions, because the coefficient of restitution is not equal to 1, therefore there's some energy loss in the collision, and it is assumed that this damps their relative velocities. And after all, what you're left with is particles that basically stay on top of each other because they damp their relative velocities. That's the only thing that happens. So what's not included here is this randomizing effect that you get when the collisions are marginally collisional. So just want to make a point that this one is different from this one. Okay, so at some point the system will be marginally collisional, and we can argue when this happens. I'm not sure. But when it is, then it's pretty hard to model, because we really need to know what every single particle does. It's like a plasma physics problem. It's not like you have a fluid where you can actually have a pressure term. Right? Some particles will collide, some others don't. So it's hard to model. What will happen in the first approximation is, first of all, the collisions will randomize the velocities, but they will also cool it down if the coefficient of restitution is small enough. Okay, so that was the negative part of my talk. Now comes a bit more positive things. So I'm going to show you how we can actually do this, and how we can do this in a mathematically well-defined way. So we're doing simulations, and we're simulating a scaled system. We still have to reduce our number of particles dramatically, because we can't do all the 10 to the 24. And we also do it in a shearing box, which helps a bit. And then the idea is that in this scaled system, we keep all important timescales that are in the system exactly the same as they are in the protoplanetary disk. So we're not assuming that a particle represents a distribution of smaller particles. We're just saying that each particle has the same timescales associated with it as it would have been if it were a real meter-sized particle in a disk. And these timescales are the orbital period, the gravitational collapse timescale, which just corresponds to keeping the surface density fixed, the stopping time, and especially the collision timescale. So the collision timescale is exactly what you have in a protoplanetary disk. Okay, so let me go back to my first plot. of the orders of magnitude. So this is what we had in the beginning. And now we're moving to the scaled system. So there are a lot of things that change. The number of particles goes down, as I said. And when the particle number goes down and I want to keep the surface density fixed, the mass of each particle increases, and therefore gravitational scattering could become important. So you see it went from 10 to the 21 to 10 to the 4. So we have to keep that in mind. Whenever this gets close to any other scale in the system, then we have a problem. Because in a real disk, this is not important, so we don't want that. I'm keeping the stopping time the same as it is, just fixed for each particle, one orbit. And I'm also fixing the collision timescale to one orbit. Now this is a bit artificial, it should be a bit more, but I'm just fixing it artificially to show you what happens when the timescales are all of the same order. So once we fix the collision timescale, we automatically fix our particle size. The collision timescale is calculated like 1 over the cross-section times the velocity dispersion times the number density. Now the velocity dispersion and number density are fixed, so we can calculate the cross-section of our particles. And that fixes our size to about 10 to the 6 meters. And also note that the filling factor goes up quite a bit. The filling factor is the volume of all my simulated particles divided by the volume of the whole box. So when the filling factor is 1, then I would have just particles in that box with no free space around it. So whenever this gets large as well, we have a problem. So we need to keep track of this one and this one here. Oh, and yeah. The nice thing about this system is that it's mathematically perfectly well defined. There's no free parameter except the number of particles. So we can't adjust anything else if we fix the timescales. And that's I think, a very nice property that isn't there if you use superparticles, for example, where you have to model the sub-physics in one way or the other. Here you don't, it all comes out automatically. Okay, so we've done some simulations. Don't go into details. We use a Barnes-Hood tree code to simulate the gravity of the particles. And besides the gravity, we only have the gas track. There's no feedback onto the gas from the particles. So there's the gas track. And we've got some random excitation from the turbulence. We're not modeling the turbulence exactly. We just imply some scale-free noise. So the nice thing is for the Barnes-Hood tree code is that we can reuse the tree to detect collisions as well. So our whole code runs like n log n, which enables us to do a few million particles. So we detect collisions by checking each time step if two of those particles are overlapping, and if we are checking that the amount is very small, so this limits our time step. But when they overlap, we resolve the collision by energy and momentum conservation. And we can add a coefficient of restitution if we want to make it more realistic. Now, when we simulate the superparticle approach, we need to have another parameter in there, which is the smoothing length, or the grid size if you have an FFT method. Because if you don't have a physical size and your particles get close, then your gravitational force will get huge. And to avoid that, you have to add a smoothing length. But note that this adds a free parameter to the system. So first of all, these are simulations. In 3 dimensions, you see the particles from above. And these are simulations with superparticles. So there are no physical collisions in here. And we've got this free parameter, the smoothing length. And what I'm showing you here is this time series of plots, one for a very small softening and one for a larger softening. And basically the result is that it depends on your smoothing length what you get out. If you have a small smoothing length, you're more likely to clump. If you have a large one, you can't clump because your structures here are already of the size of your smoothing length, and that supports you, so you won't collapse that easily. Now, this is approximately the size of a 128 grid. So if you use an FFT method of 128 cube, then this is looks more like this. So these are the simulations from our scaled system. And here we only have the number of particles as a free parameter. So if the number of particles is not large enough, then we have problems because of this filling factor is getting too large, as I showed you before. So we need to be above a threshold, which is about 100,000 particles. And then this filling factor is always small enough so that we can actually resolve it. And then the results do not depend on the particle number anymore. You can see that it clumps at the same time. The clump statistics are the same. And yeah. I can show you this more quantitatively. We use a velocity dispersion as a measure of the clumpiness of the system. So what happens in those plots is that we start off from an equilibrium here, and then we push the system into a gravitationally unstable regime. So we do this by increasing the damping, which means the velocity dispersion goes down. And once it goes down, Q becomes of the order of 1, and we collapse. And as soon as we collapse, the velocity dispersion rises, because it's higher inside the clump. So whenever this curve rises, it tells you when the clumping occurs in your system. And you see that in the top picture here, which is for the superparticle case, that it first of all depends on your number of particles, and it depends on your smoothing length. Now you can do a trick, and you can change your 2 free parameters at the same time. You can choose the smoothing length to be n to the minus a half, where n is the number of particles. In that case, you get actually the best results, which are almost independent of those 2 parameters when you scale them like this. But again, you don't know the coefficient here in front. You can choose whatever you want to, and you can, these 2 parameters determine the outcome. Now, if you compare this to our scaled system, it looks much better, because here we only have the number of particles, and the curves are basically on top of each other, meaning that they clump exactly at the same time, and yeah, everything is what we call converged. So there's no free parameter anymore. Okay, so I'm already coming to my conclusion slide. So there are 2 points I want to make. First of all, the planetesimals can become marginally collisional in the disk. And if they do this, then the superparticle approach might not be the right way of doing it. The scaled system that I've presented to you and will be published in a paper soon is one way of doing it. It's working very well. You can extend this. You can do a Monte Carlo type of method by not actually resolving every single collision, but you let particles overlap each other, and then with a given probability assign a collision to that event. Has been done similarly in that paper, also for different application. That can speed things a bit up if you want your code to be even faster. But this will again add more parameters. You need to fine-tune this probability whether you assign a collision or not. And in the scaled system, it just pops out automatically. So if we are in this regime that we are marginally collisional, then the result is basically very simple, because the collisions will randomize the velocities at some point, and this will prevent clumping in some. It will prevent the clumping in some way or the other. We can talk about the order of magnitude of which it will prevent. It's probably just an order of magnitude effect, but if the result is that you either clump or you don't clump because of this order of magnitude effect, then it will be important. Okay, so there are 2 things. First of all, we need to really know when the system is marginally collisional. And then we need to better understand what happens in a collision itself, right? Those meter-sized particles are a bit mystical, at least to me. I don't really know what they're made of and what happens during a collision. And as long as we don't know that, there's not much to do. So there's one more thing. If you've ever not watched a keynote from Steve Jobs, you know that now comes the best thing. So you can do an experiment. And you can just collide a meter-sized particle with another meter-sized particle. It has been done by those people here. So what they've done is they bought 2 spherical rocks from China for $20,000, put them on a crane, and then they let them collide to see what the outcome is. Now, obviously, this is probably not how our meter-sized particles look like, right? But it's the first guess. So this is the highest impact velocity run they could do. They are, I think, 3 meters per second impact speed. And yep, let's just see what happens.
Yes.
So you see that basically nothing happens, right? They just bounce off each other. So the bounce was actually so good that you couldn't even see an impact point. That there was no crater, there was nothing, no damage to the spheres at all, which I find rather surprising. So they were actually trying to break those balls by smashing them together, but they couldn't because they were so stable. So, yep, that's what I wanted to say. Thank you very much.
So making a big point out of the meter-sized particle. But in fact, if I'm checking your parameters, your particles would be called in our context like 6-meter particles, because your omega tau f is pretty large with having 6. So the typical particles we were using in our numerical experiments were, in comparison, 10 times smaller. So having a friction time with the gas which is 10 times smaller. This is why in most of our simulations, and we are checking this, the dynamical interaction with the gas is absolutely overwhelming. So and we are also checking at the same time when collisions, just in your way, are starting to be important. And this is basically already halfway down to the planetesimal. So once we already have our condensation and the thing has almost formed, it's already pretty deep in its potential well, then suddenly we also see that now collisions become important, which arguably we are not treating very nicely by having the superparticle approach. But I think even if we would have a very a negative approach and then just say that this RMS velocity will push things out again, you're already so far down in the potential well that you will not be able to escape from this. So have you done experiments with an omega tau f of, let's say, a half or even smaller? What happens then?
Well, I agree with your point. I mean, I'm not sure when this happens, and if you say that it happens far down in gravitational collapse, I have to believe you, because I'm not doing the whole simulation. Now, when it happens too late, then it will not matter. But you have to be careful. If you say they're in a potential well, and your potential well is basically one grid cell.
No, it's not.
But yeah, that would be my concern. That if your planetesimal form on a scale that is comparable to the grid scale, and you're not modeling the collisions, then you're pushing particles into that grid cell, and they cannot come out. Whereas I think it would be more realistic, even if it happens very late, if you add collisions, which would then make the velocities more isotropic and add some effect to that. So even in that case, I would say it matters. I haven't done simulations in that parameter regime, but maybe you can talk about this and you can tell me what I should exactly use.
Yes. How do you control and choose the initial momentum of your particles and the initial energy?
You mean our initial conditions?
Yes.
So I didn't want to go into too much detail because the initial equilibrium is quite hard to get. It took us a long time. So we're integrating the system for a very long time. So this is, you see, 30 orbital timescales. And this is actually a stable system up till here. We do this by having this damping force, and we have an excitation force that comes from particles, that comes from the turbulence. And those two balance to give us a stable equilibrium, and then we turn a parameter slightly to push it into the gravitationally unstable regime. Now we think that this initial condition gives us the right velocity distribution because it's a non-trivial initial state. It's marginally unstable. You've got some epicyclic motion going on, and there are also collisions which randomize already in that regime your velocity field. So yeah.
Just one comment is that in the simulations that that we've done with Anders, one of the differences with what you're doing is that the self-gravity is actually not responsible for creating the clumps. You sort of showed that the clumps were created by these other mechanisms, and then once self-gravity is included, there's actually no instability necessary. It's just already gravitationally bound. So that's different from what you're doing, which is also very interesting, which is self-gravity itself creating the clumps, more of a standard true gravitational instability.
But you're never going to create a clump if you don't have self-gravity. I mean, it doesn't make sense of talking of a gravitationally bound object without self-gravity.
No. So the point is that if you ignore self-gravity, you can have other processes that bring you towards a density that would be gravitationally bound.
Okay.
That's what seems to happen. But in cases where the clumping is not so strong, then approaches like this are going to be more and more relevant.
Okay. It would be the same argument for the collisions then, but I mean, it doesn't matter how you create your overdensity, as long as it's dense enough so that collisions become important, then I would have the same argument chain. But, yeah.
Okay, time for lunch, I think. Thank you again to Hanno and the